Welcome to Study Loop.
Hello everyone, today we're doing chapter 14, problem 14, and this question asks us that given these following compounds, determine how many numbers of NMR signals you would get and how many peaks for each of these signals you would have on your NMR spectra. So it's asking for how many chemically unique protons will there be and what are their splitting patterns that you will see on your NMR spectra. So let's start with A being left side. So once again, this molecule is achiral, so it has an internal plane of symmetry. So what happens on the left side will happen on the right side. So we know that to determine the number of chemically unique protons, we should draw out all our protons to help us visualize what's going on. So we see that these terminal protons, these 3 protons on the CH3 bonds, are directly bounded to another carbon, and the same thing is true for the right side. So we know that these 6 protons, 3 on each side, are chemically identical to each other, and these 2 protons on both sides are chemically identical to each other. So we have 2 unique NMR signals. However, what would their splitting pattern be? So to determine the splitting pattern, you need to remember the n plus 1 rule. So you have n being the number of protons you're interested in, and you have plus 1 for your neighbor. So if I were to reiterate that, so if I'm looking for these 3 protons, n is your neighbor, and then you do a plus 1. So let's write that out actually. So we have, so your splitting pattern equals neighboring proton, number of neighboring protons plus 1. So what does that mean? That means, let's say I'm interested in these terminal protons here in blue. So if I'm interested in these terminal protons in blue, I see that these 3 protons that I'm interested in, their neighbors, so this carbon that's bound to these 3 protons is directly bounded to a carbon that has 2 protons bound. So there is 2 neighboring protons, and then do a plus 1. So I know that these protons, these 3 protons that I'm interested in, would show as a signal of 3 peaks. That's what we call a triplet. But now these two protons that I'm interested in are bound to a carbon that's directly bounded to a carbon that has 3 protons bound to it. So these 2 proton has a neighbor of 3, and you do a plus 1, so you would have a quartet here. So we had 4 signals. This is what we call a quartet. This is what we call a quartet. So some might be asking, well, in fact, we have 6 protons here in these methyl protons, and they're neighbored by 4, so it should be 4 plus 1. So we would actually get a pentet, but a quintet, sorry. But remember that internal plane of symmetry. So because we have that internal plane of symmetry, you should only be investigating one side because each of these sides are copy paste of each other. So it's kind of redundant to investigate both sides when you have internal plane of symmetry. All you need to do is just investigate one side, and that will be true for your opposite side. So in this one, we have a triplet and a quartet. This triplet represents these 3 protons splitting by these 2 neighboring protons. 2 plus 1 equals the triplet we see. And these 2 protons, they're neighbored by 3 protons. So then you have a 3 plus 1, which gives us a quartet. But actually something I didn't mention is that also neighboring this carbon, not only is this carbon that's bound to these 3 protons, but it's also this carbonyl carbon here. But this carbonyl carbon here has no protons attached to it. So this is not included in any splitting for these 2 protons here. But it may so be the fact in these problems that we're going to do now. So if we do this second problem B, we see to identify the number of unique protons, we need to determine how these protons look. So we see that we have a central carbon here that's bound to a carbonyl carbon and has 3 protons. So we can say that this is one unique proton. We have another terminal carbon here that's bound to an electronegative oxygen atom. So this is clearly in a unique chemical environment. So these are 3 unique protons. Then we have the CH2 that's bound to another CH2 and bound to electronegative oxygen atom here. So we can say that this is one unique set of protons. And then we have a CH2 here that's also bound to CH2 and an oxygen electronegative oxygen atom. But this electronegative oxygen atom is also bound to a carbonyl carbon, while this one is bound to a methyl. So we know that this is going to be unique for this CH2 is unique from this CH2. So we know that that's going to be unique too. So now let's determine the splitting pattern. So let's determine the splitting patterns of these blue carbons here. So we have 3 protons bound to this carbon. So we need to determine how many neighboring protons are next to it. So we look 1 carbon adjacent to the central carbon, and we see that we have a carbonyl carbon. Attached to this carbonyl carbon is 0 protons. So your neighboring is 0, and then you have a +1. So 0 + 1 equals is a singlet signal you will see for these 3 protons. So these 3 protons will show as a singlet. Because remember, your neighboring proton is 0. 0 + 1 equals 1. So then we just have a singlet. And now let's look for example, these 3 protons here at the terminal end. So we are bounded to a central carbon atom that's neighbored to an oxygen. This oxygen has 0 protons bound to it. So we have neighboring protons of 0 + 1 equals, once again, another singlet. So we have here another singlet for these green protons. But now let's look at these blue or these black protons here. So these black protons are bounded to the central carbon atom here. So the central carbon atom is neighboring to an oxygen that has no protons attached to it, but the central carbon atom is also bound or is neighboring to another carbon atom that has 2 protons attached to it. So in total, we have a neighboring of 2 protons. So 2 + 1 equals 3. So we have a triplet here for these 2 black protons. Now for the red protons, we have a neighboring, so we have these 2 protons bound to a central carbon. The central carbon is bound to an oxygen that has 0 protons attached to it, and is also bounded to a carbon that has 2 protons attached to it. So in total, we have a neighboring of 2 protons, so 2 + 1 equals 3. So we also have a triplet for these red protons as well. And in total, we have 1, 2, 3, 4 chemically distinct protons here. Now let's look at the third example. So the third example, if you look at all of these protons, well, we can very obviously see that we have 2 distinct chemical protons. One being this terminal methyl and one being from the carbonyl carbon here. So if we look at determining the splitting pattern, so if we're interested in these 3 protons, we see that this central carbon that has these 3 protons bound to it is directly bounded to another carbon here. This carbon has 1 proton attached to it, so it has 1 neighboring proton, so 1 + 1 equals 2. So these 3 protons are represented by a doublet. So here we have a doublet for these 3 protons. Now for this green proton here, so let me actually rewrite that in blue so everything's organized. So these 3 protons are a doublet, while this single proton, so we're investigating this 1 proton. So this 1 proton will have a splitting pattern that is the number of neighboring plus 1. So it's bounded to a carbon that's neighboring another carbon. That's this carbon, this neighboring carbon has 3 protons bound to it. So the neighboring equals 3, 3 + 1 equals 4. So we have a quartet here. We have a quartet representing the single proton here. Now let's look at the last example. So this last example, let's determine the number of protons. So here we have let's determine the number of unique protons. We have these 3 protons being unique from these 2 protons, which is also unique from this single proton up here. So now let's investigate the splitting pattern of this single proton up here. So this single proton is bound to a central carbon that's neighboring this carbon here that has 2 protons bound to it. So we have 2 neighboring protons, so 2 plus 1 equals 3. So this red proton, this single red proton, would be represented as a triplet in our NMR spectra. Now these green protons are bounded to the central carbon atom that's neighboring this carbon atom that has 0 protons attached to it, but it's also neighboring this carbon atom that has 1 proton attached to it. So in total, we have 1 neighboring proton. So 1 plus 1 equals 2. So these 2 protons would be represented by a doublet in our NMR spectra. And now if we look at these terminal protons here, so we have 3 protons attached to this carbon. This carbon is directly bound to an oxygen, and this oxygen has 0 neighboring protons attached to it, so we have 0 plus 1. So these 3 protons will be represented by a singlet in our NMR spectra.